In this video 9, we are going to study about dipole. Dipole means two. Di means two. Before that, we have learned about electric force. We have learned about electric field. Now we are moving to the next concept called dipole. What is a dipole? Dipole is two equal and opposite charges plus q and minus q separated by a distance, a small distance. This is called a dipole. But where do you find this dipole in real life? You take a hydrogen atom. Hydrogen atom has a proton which is a positive charge and it has an electron revolving around it, and this sets up a dipole. We are going to draw a line like this. It is only for our reference. Otherwise, there is no line joining them. It is electrostatic force which is acting at a distance. Okay, so the electron is revolving around it. So the distance of separation is so small, it's around 10 power minus 15 meter. Now, let us take for example a model of dipole. There are two charges, equal and opposite, and separated by a distance, right? And this sets up a dipole. Now, dipole has something called dipole moment. Now, what is a dipole moment? Dipole moment is one of the charges multiplied by the distance of separation. Now, P, we use the symbol P as the electric dipole moment. One of the charges is Q, and I take the distance of separation as 2a for certain reason. I can take it as a, but I have taken it as 2a for a specific reason. So, the dipole moment P is equal to Q into 2a, and being 2a is also a vector quantity, which is a displacement, and P, the electric dipole moment, is also a vector quantity. So, electric dipole is two equal and opposite charges separated by a small distance. Charge multiplied by the distance, coulomb into meter. Coulomb meter is its unit, and it's a vector quantity, and in which direction the dipole moment will act. Look here, this is going to be, let us say, positive. Positive will be repulsive, and negative will be attractive, and you will find that the dipole moment will act from negative to positive, right? It is going to be acting from negative to positive direction. Now, we go to the next concept. If I take a dipole and place it in an electric field, an uniform electric field. The uniform electric field is drawn as a straight lines. They are all parallel lines. Now what I do, I am going to place a dipole in the electric field. When I place it in the electric field, you will find that the positive is this side, right? Electric field starts from positive and ends in negative. So I place it like this. So there is a force acting on the positive charge, that is F plus, and there is a force acting on the negative charge, which is in the opposite direction, F minus. Two forces are acting, they are equal and opposite, but there is no, so let us say, what is the net force acting? F plus is QE. We know E is equal to F upon Q naught. So I have taken QE, which is positive, and for this one it is negative charge into electric field, right? Plus and minus cancel each other, so you have F net force is equal to 0. When net force is 0, that means there is no translatory motion. There is no translatory motion. The charge, the dipole is not going to move like this now. Why? Because the line of action on this charge and this charge are not same. What do you mean by that? The line of action, see the dipole is here, and one force is acting like this, another force is acting like this. If the two forces are in the same way, equal and opposite, then the body will be in equilibrium and there is no translative motion. Instead of that, since lines of actions are not being same, it is being different, it will set up a rotatory motion. You can watch it very carefully, right? When it places like this, and a force is acting like this and acting like this, and it will set up a rotatory motion. Very clearly we can see a rotatory motion is being set. So there is no translatory motion, net force is 0, and there is a rotatory motion. There is a turning effect, which means there is a torque is being set up. Now we have to find out the torque acting on a dipole placed in a uniform electric field. So let us see how we derive that equation. So remember, dipole is di means two. Two equal and opposite charges are being separated by a small distance. Okay, fine. Now let me move on to the concept of torque. Torque we represent by the symbol tau, which is equal to force multiplied by perpendicular distance. Right? Now what is the force acting? QE. Okay, one of the forces. So let me take QE multiplied by the perpendicular distance. Let us watch carefully. Okay. Now this is the electric field and this is the dipole. There is an angle between these two. The angle between the electric field and the dipole axis is 90 degree. Right? Now, the angle is going to vary as it rotates. It comes from an angle, arbitrary angle theta. Okay, now if I place it like this, you find that 1, 2, 3, 4 lines of forces are passing through. As the dipole rotates, you see what is happening. The number of lines of forces passing through is decreasing. So we need to take the perpendicular distance over which the electric field lines are passing through. So this line we need to calculate. This angle is theta, the arbitrary angle, and this is the perpendicular. We know that sin theta is equal to perpendicular upon hypotenuse. Now perpendicular is equal to hypotenuse into sin theta. Now what is the hypotenuse? This is the distance of separation between the two charges. That is 2a. So let us substitute it 2a into sin theta. That is the perpendicular distance. Let us substitute it in the formula of the torque. Tau is equal to F into perpendicular distance. F is QE in the electric field and the perpendicular distance is 2a into sin theta. Now we know by definition that Q into 2a is electric dipole moment. P is equal to Q into 2a. So I will put it instead of Q into 2a, P into E into sin theta. And that is the formula for the torque setup, where theta is the arbitrary angle. Place it like this now. You move it, theta goes on changing, and then theta becomes 0. When it is 0, it is in stable state. When it is here, it is unstable state. Fine. Now the formula is tau is equal to P sin theta. In vectorial form, tau is equal to P cross E, where all these factors are vector quantities, right? And it is a vector product because the angle theta, sin theta requires direction. So we learned today about the dipole. It's also part of electrostatics. In this video 9, we have learned about dipole, and also we have learned about what will be the torque setup in a dipole when placed in a uniform electric field. Remember, dipole is two equal and opposite charges separated by a small distance. Thank you.